Hi there, this is Matt Heffernan, and welcome back to my channel. Today's vlog of this week is going to be in response basically to my, not my last one, but the one before, the main episodes that I do that are more scripted and edited. And the biggest video I've had so far, the first week was bigger than the entirety of any video I've ever had before, and that was looking at the Z80, the Zilog Z80. And that has just really taken off and has driven a lot of new subscribers to my channel. If you're one of those new subscribers, welcome. And in case you haven't seen one of these episodes before, this is Slithy Vlogs, and it is going to be more stream of consciousness, off the cuff, less scripted, less edited, and just me more pontificating about different things. And but there's still going to be some structure to it. I don't just go totally off the handle for any of this. So this week's vlog is going to be a much requested and really kind of necessary comparison between the 6.5 CO2 and the Z80. And as I said in the original Z80 video, yeah, I do say Z80 because Zilog is an American company, or at least it's the remnant of an American company at this point. And although it has found great success in British systems like the Spectrum, which is the Sinclair ZX Spectrum, because in the UK they say Z, as they do in pretty much every English-speaking country except for the United States. And so that's where you get a bit of disconnect, but I think we can all roll with that and agree with that, even though somebody outside of the US may refer to the Zilog chip as the Z80 as well. I will not. I'm going to just call it the Z80. And but meanwhile, the 6.5 CO2 is, of course, the modern CMOS version of the classic 6502 processor. It is what's being used in the Commander X16 that I have a lot of videos for. That is a new retro computer being brought to the market by David Murray, aka the 8-bit guy, and a bunch of other folks in the larger retro community. And so I have a whole assembly language tutorial series about that. That's starting to wrap up. I'm getting into the last couple episodes now. But you can go back and watch it if you're really curious. If you're coming as a Z80 person into this video, this may serve as a good introduction also to the 6.5 CO2 specifically, and perhaps the 6502 family in general. But definitely you want to go back to that series, how to program an assembly language for the Commander X16. And I've got 17 episodes already out, and there's a whole lot to learn there, and that's really going to be the model for my Z80 series. I may not go like quite so far back in terms of really explaining all of those details necessarily, all of the particulars of assembly language programming and how it differs, because I definitely want to lean on some of that older content. But I still will be going at it. I'm going to assume generally that somebody going through the Z80 tutorial is somebody that has some programming experience, perhaps with BASIC, or maybe even frankly, a better language like C or Forth or something like that. And that, well, here's how assembly language works, and specifically for the Z80. And as we're going to see in this video, these are two very, very different instruction set architectures. And even though they're both 8-bit processors, they really couldn't be more different. And I think we're going to see in this video what those differences are, how you accomplish some things in different ways, and with very different syntax, and quite often in different orders of operations. And then at the end, well, what do we think? Well, which one really wins out? And well, we'll see. We're going to get my opinion, but I of course welcome your opinion. Please put it in the comments. And if you're not, again, I'll remind you at the top, please subscribe to my channel, and you'll see some of the follow-up to this. And if you click that bell, you'll get notified as soon as the first tutorial episode for the Z80 comes out, along with all the rest of my content. So let's get right into it. So the 65CO2, very simple processor. The original 6502 was developed for the express purpose of being a low-cost microprocessor. It is, of course, it's an 8-bit processor, but the intent was to make it as simple as possible, to use as few transistors on the chips as possible, so that you could, even today, you don't have to have like a 10 nanometer process to make a 65CO2. There's so few transistors required. You can still use a much cheaper, wider process, and really, generally, people aren't running 65CO2s at 4 gigahertz. We're talking like, of course, I now that I'm getting into this is something that I didn't write down on my slides or notes, and what the actual top speed is, but I know it's in the neighborhood of 14 megahertz. Of course, the Commander X16 runs at 8 megahertz. But so yeah, it's plenty fast enough. You don't have to have teeny tiny transistors to make it, and you don't need a whole lot. And all of the opcodes, all the unique instructions within the 65CO2 all fit within a single byte. And in fact, there's a whole bunch of potential opcodes that aren't even in there. So only 211 different opcodes that are used for the 65CO2. And so every instruction, of course, there's those weird in-between ones. They all act as no-ops within the 65CO2. Older processors in the 6502 family had undocumented behavior for some of those, but the only weird thing with these other no-ops, other than the main no-op at hex EA, is that some of them actually can take operands that are also ignored. So nothing happens, but the program counter may actually move ahead more than one if you use one of these undocumented ones. And then when we look at the Z80, well, it's a much more complicated processor. There's a lot more going on. There are fully 801 opcodes, because opcodes can be more than 1 byte. In fact, they can be up to 3 bytes. And then you can see here the purpose of the Z80 was to dominate the Intel 8080 in the market. So the Intel 8080 had a lot of limitations, and Federico Faggin, he knew those limitations because he designed those into there. He was the lead engineer at Intel, and when he started Zilog and created the Z80, it's like, well, we're going to overcome those limitations, and we're going to make as comprehensive an instruction set as we can for an 8-bit processor, and still, be able to fit within the processes of the time. It's gonna be, we're still talking, it's, the mid 70s, and the TRS-80 was out by 1977. So you did not have nano technology back then. You're talking about pretty fat transistors by today's standards. So, but yeah, cramming 801 instructions in there, it's pretty great. And so you would think that, well, wow, I mean, they're both 8-bit processors. They can both deal with memory 8 bits at a time. They have an 8-bit data bus externally and internally. In fact, the weird thing is with Z80, some of the components on the internals are actually just 4 bits wide. But you would think that, well, I mean, the 65CO2, it's so simple, and there's so few instructions. It's practically a RISC processor. It's like a reduced instruction set, but not for like in our modern context of RISC. It's more just because it's just a small processor. It's reduced because it's small, not because they're doing things like, say, an ARM or a a Spark processor or a MIPS, or rather a MIPS processor, what they would do in terms of trying to make sure each operation happens within like a consistent sequence, so that you can pipeline it and do all this stuff a lot more easily than if you have all these different kinds of widths of instructions. Well, you have all different kinds of widths of instructions. It can be between 1 and 3 for any of these instructions. So it's not really a RISC processor in that sense. But you would think, well, because it's so limited, that certainly the Z80 could do anything the 65C02 could do in its vast number of instructions. Those 801 instructions, you got to have pretty much all of these covered, right? Well, not quite. Only these shaded ones here. These blue ones are, and that's it. All of the ones that remain unshaded, those are unique to the 65C02 when you're compared to the Z80. The Z80 can't do any of those other instructions, any of those other operations on registers and or memory without doing at least 2 instructions. And so it's kind of crazy. It's how could they be that different? How differently could you make an 8-bit processor? Well, let's get right down to the nitty-gritty. Let's look at the addressing modes. But before we do that, just to kind of illustrate how many different kinds of opcodes you have for the Z80. So you can see up here in the upper left, we have this the main sort of first byte of the opcode. And for out of 252 cases, it's just going to be that single opcode, single byte opcode. But you have 4 of those could result in a secondary or possibly a tertiary opcode to go along with it. So you can see at CB, you could have CB as the first part of the opcode, the first byte of the opcode, and then there's another 256 opcodes after that. So it could be CB and then literally any 8-bit value after that, and that would be a unique valid opcode for the Z80. Going on through DD, if hex DD is the first byte of your opcode, then that means that, oh, well, then you're at least going to have 1 more byte in your opcode. And then if that second byte is CB, then guess what? It's going to be a 3rd byte for that opcode. So this branch here, this upper branch that you see on the upper right branch, those are the IX branch, basically, of the instruction set, where the HL register gets swapped out for the IX register, and then you can do all these different indexing modes in that. And then the sort of the middle one coming out of ED, if ED is the first byte of your opcode, then you've got these just a few in there, not as many as the first one, because what that's going to do is these are entirely different. It's kind of like the CB opcodes, where you're coming up with a whole new set of instructions in there. And then FD is going to be the same as DD. Instead, we're substituting the IY register for the HL register. And then if that second byte is CB, then it's going to go to yet a 3rd byte of that opcode. And so, yeah, whole bunch of instructions, all those 801 different opcodes of 1 to 3 bytes just for the opcodes. That doesn't include operands, because then you could have in these could have 1 or 2 bytes worth of operand data after the opcode. So it gets, You definitely are solidly within the CISC territory, the comprehensive or complex instruction set computer. So, as I said, we're going to get right into addressing modes. This is the basis of our comparison. So if you've gone through my 65CO2, the Commander X16 assembly tutorial series, I've gone through all these addressing modes before in that series, and in fact, in the the very second episode, I go into each of those addressing modes in detail. So, if you're a Z80 person and don't understand those 65CO2 addressing modes, based on the sort of quickie intro I'm going to give to them in this video, I go into greater depth in that video. So check that out. So first of all, the implied mode. So for the 65CO2, we have 37 opcodes that are the implied mode, meaning that there's no operand necessary. And we could have instructions like wait or return from subroutine, and even the mnemonics are just going to be that abbreviation for the instruction, and that's it. Just and then, of course, you're just going to have, for all 37 of these opcodes, it's just going to be that one byte, that opcode, and that's it. No operands after that opcode in the machine language. For the Z80, it's more complicated than that. So what you have are all these different ways of having implicit opcodes. And first off, you can have ones that are just like the 65CO2, where you have these implicit mnemonics, and they're just 8-bit opcodes, and there's 14 of those in the instruction set. So 5.56%, and here we have actually direct corollaries of those opcodes that I put at the top for the 65CO2, which would be halt and return, work the same as wait and return from subroutine. Those were little shaded in boxes in that first table that we saw. And so so then in those cases, those 14, it's just like that. It's just an instruction. There's no, in the assembly language, there's no operands written out, and in the machine code, it's just a single byte. But then you have some of these 16-bit opcodes that are also implicit. And even the mnemonics are implicit, so you're kind of abstracted in the assembly language, where you don't necessarily know that halt and return are 8-bit opcodes, and that negate and load, increment, and repeat, which is LDIR, that these are 16-bit opcodes. And there's 22 of these like this, where there is the assembly language has no operands, but it's 2 bytes just for those opcodes, but they're still fixed. It's still an implied instruction. But then we get into the other hairy detail, is that the assembly language for Z80 can have operands. They appear to have operands, but in reality, those are sort of hard-coded operands into in those opcodes, and including some of the 8-bit opcodes. In fact, 188 of those 8-bit opcodes, when you write them out in the assembly language, that assembly language mnemonic has operands in it, and we're going to see how some of that works. And then moving on to the 16-bit opcodes, fully 393, that's 80 or more than 81% of the 16-bit opcodes don't have any operands in the actual machine code. They are implicit opcodes, but again, in the assembly language, we actually have the mnemonic where it is going to be the instruction abbreviation and then some arguments. But again, those are all specified by the opcode. And then finally, in the 24-bit opcodes, every single one of them, all 64 of the 24-bit opcodes, are actually rendered in assembly language as having operands, but you never have an argument with these 24-bit opcodes. And when you're talking about the machine language, so it's just going to be the 3 bytes and that's it. You don't have to worry about more stuff. So yeah, let's take a look now here. So if we consider all 5 of these situations as being implied mode, and even though technically if you were talking about the Z80 assembly language, these aren't really all implied implied mode opcodes. Only those first 2 cases of the implicit, where the actual mnemonics themselves are implicit, that those are only the ones that are considered implied, those 36. But in reality, 757 of the opcodes are implicit. There's no operands in the machine language. And so that's 85%, over 85%. So now let's consider that in the 65CO2, that only just over 17.5% of the time, okay, fine, you don't need an operand, but otherwise you're going to have an operand. So there's going to be, it's really expecting you with the 65CO2, and this is a theme we're going to see throughout this, that the 65CO2 expects you to interface with memory a lot more than the Z80 does. And as we saw in my my first Z80 video, one of the big features that was added to the Z80 was this automatic dynamic RAM refresher, the DRAM refresher, and that allowed you to add much cheaper RAM to it, because DRAM compared to static RAM or SRAM, it's a lot cheaper. It's a lot fewer transistors to implement dynamic RAM than static RAM. But static RAM is a lot faster because it doesn't need to be refreshed, and just the way that it works, that you can actually do things more parallelized with static RAM. And so for the 65CO2, you really need to have that static RAM. You need to have very fast RAM because you don't have a lot of time in those instructions to fetch stuff from memory. So you really have to make sure you're using SRAM with 65CO2, and that's why it then just depends, because the processor, the whole instruction set, makes the assumption that you're just going to be touching memory a whole lot. But no, with Z80, it's like, all right, you're going to fetch your instruction from memory, and then that's it. Everything else is not going to deal with memory at that point. So that makes, or at least if it's not going to deal with memory, it's not going to deal with an arbitrary address. That it's going to deal with an address that is not stored in memory, but an address that is stored in a register. So definitely really taking advantage of the registers. And that's what, that's what actual modern RISC processors do that too. You get a ton of registers to make things just snappy and predictable. So let's take a look now at these Z80 addressing modes that are not implied. Technically, these are not implied addressing modes because their mnemonics require operands, but the opcodes themselves are implicit, or at least sometimes they're implicit, because as we'll see, you don't have cut and dry singular addressing modes for these different opcodes, because most probably most of these opcodes, the mnemonics for them have 2 arguments, and there's 2 operands being passed to it, comma separated, which you only saw with indexed, or mostly just with indexed addressing modes in the 65CO2. And so, but now it's like, well, so now each of your operand can have its own addressing mode, and so you have all these different weird combinations. But here we're just considering that we're talking about when we're counting the instances of these addressing modes, we're saying that at least one of the operands uses this addressing mode when we're talking about these counts. So let's get right to it. Of course, the big one is the register. So the register addressing mode means that either you have a single register as your operand, or in your two operands, one or both of them could be registers. And in here I have an example where all of the operands are registers, and these are all different ways of doing the register addressing mode. And so the registers, as we can see here, I've got that chart back up. There's a whole lot of registers. And in fact, you have the alternate registers, which you can sort of swap out with the main registers at any time. So you can have like a reserve set, kind of like a hockey team, that you can you have all your starters come off the ice at once, and you put in the second team right away. So that's all these different registers. And then of course you have some are overloaded, say like B and C can be individual 8-bit registers, but they can be combined into a single 16-bit register called BC. And so, yeah, all these examples, like here, we're loading A with the value in B, or we're adding the value in BC into HL. And so we're adding HL and BC together and storing that in HL. Or we're incrementing the C register, just an 8-bit increment, or we could do a 16-bit decrement with like DE. And so there it becomes powerful, where a lot of these things, like especially these 16-bit adds and the increments and decrements, you can't do that without with single instructions in the 65C02. It's all strictly 8-bit instructions. And so you have a lot of this stuff being abstracted away from you, even in the assembly language with the Z80. And so it can make your code end up being a lot more terse. It requires fewer instructions to do that. So that's really nice, right? So yeah, and then you don't have to mess around with carry bits for doing these things. It definitely makes it a lot simpler. So moving on, there's the register indirect mode, and that's where you have an address register as one of the operands, but it is surrounded by parentheses. And these are the kinds of instructions that will interface with memory, even though you don't have an actual memory address in the instruction. You're not passing, you don't have a machine language operand of an address, whether that's like a 1 or 2 byte, where you have like the 0-page mode in 65C02. No, you in a lot of the cases, you need to load up one of those 16-bit registers, one of the registers that can take a full 16-bit address, and then you use the register indirect mode to be able to interact with memory through that, rather than having the actual address stored in your program for that instruction. Then we have modified page 0. So, of course, what we call the 0 page for 6502 is called page 0 for the Z80, I guess just to be different. Who knows? But what you have these are still implied. You're not putting a 0-page address as a machine code operand in there. That page 0 address, which is, of course, it's a 16-bit address that starts with 00 in the upper byte. You have fixed addresses that are called out by the opcodes themselves. And the only instruction that uses this is RST. And this is basically used for accessing jump tables in like the very beginning of memory. And say for the ZX Spectrum, that's the ROM. So you have you can have ROM routines there. A lot of Z80 platforms, a lot of systems use these first few addresses in page 0 as a ROM, and then have little jumping off points into ROM subroutines. And that's all this will do. It will go to the subroutine at hex 28 at that address, and then it'll eventually return from that, and it's an alternative to using call. So you don't have to pass a 16-bit address to call. You can just use this single opcode, and it can make things a little bit faster. So this is why you would have these very frequently called subroutines. If they're very frequently called, especially if they're in ROM, but even if they're in RAM, if you did have access to that page 0 as RAM, then you could put some of your most commonly called subroutine stuff that you got to call a lot. You can save a little time by putting it at one of these magic addresses that gets called out by these RST opcodes. And then we have bit. Bit is not just an instruction, it's also an addressing mode. And as far as an addressing mode is concerned, that's referring to having a bit number as an operand. And we kind of have that. Sometimes we have bit numbers are included with the instruction names rather than as an operand. There's no space between them on those on certain 6.5 CO2 instructions. But for Z80 instructions, there is a space, and it's always going to be the first operand. So for the bit instruction, we have, say, bit 3A means that, all right, well, bit 3, we're going to test bit 3 in the accumulator, in the A register. And if bit 3 is clear, we're going to set the Z bit, the 0 bit. And if it's set, we're going to clear the 0 bit. And that's how the bit instruction works. Now, the reset instruction, that also can reset a bit. It will clear a bit, and it will clear that bit in a specific register, and that can even be the virtual memory register referenced by the HL register. So you can have the address of a byte in memory in HL, and then you could just reset one of its bits. And now this is not the same as the test and reset bit instruction in the 6.5 CO2, because the reset and the set instructions in Z80 actually don't change any of the flags. The flags stay the same. So you can't use it as a set. You still have to do, say, a separate bit and then reset, and then deal with all of that. It'd do that in a bunch of with a pair of instructions. And then we have a mode. This is not like an official mode. I call it the conditional mode. And that's where you're using a flag condition as an operand in assembly language. I don't know why this isn't generally recognized as an official addressing mode, but I'm going to call it that. I'm going to call it the conditional addressing mode. And so that's where a particular flag condition, say, like in this case, the example, you're going to return if the Z bit is not set, or NZ, the NZ condition, you're going to return. Otherwise, you don't return. You just keep going after that instruction. And that's there's a lot of instructions like that in the Z80, where you can have conditional returns and conditional calls. And they all use these flag conditions as one of their operands, which is nice. It's a very convenient thing. And there's the case opposite of what I was just talking about with like test and set bit or test and reset bit, where you have to do multiple Z80 instructions to do a single 6.5 CO2 instruction. This is the opposite, where you have to actually do a bunch of messing around in 6.5 CO2 to do some of these really nice, clean, conditional instructions like return and call. But then also, of course, the jump instructions, the regular jump and the jump relative instructions also use these conditional operands in them. So it's pretty widely used. And then finally, there's another mode that I've had to invent. I had to give it a name, and I just call it the interrupt mode because that's also the name of the only instruction that uses it, the IM instruction, and where you set an interrupt mode. And so there's 3 interrupt modes, 0, 1, and 2. And so in the assembly language, you're going to have 0, 1, or 2 as the operand, but these are not immediate values in memory. These are, again, encoded in the opcodes. So 3 separate opcodes for the interrupt mode, and one for each interrupt mode. And that's how that works. So now let's get back to the more universal addressing modes. As I said, there's the immediate, and of course that's one of the next most simple addressing mode after the implied mode. And that's where you have the value that you're going to operate with actually in your code. It's not somewhere else not being referenced as somewhere else in memory. It's right there in the program. And so, of course, we have 12 opcodes for the 65C02 that do this. That's over 5%. And that, mainstays like the immediate load into accumulator. So you can just say load a hash 42, and then the value 42 will be loaded into the accumulator. That will be in there. And for the Z80, it gets a bit more complicated. Again, there's really there's like a few different variations on what are considered immediate. In fact, there's 2 separate addressing modes that are immediate addressing modes. There's just the regular immediate addressing mode, which is the 8-bit immediate, and there's 16 opcodes like that, 2% of the opcodes, and those are things like, so if you're going to load the accumulator with the value 42, you can use that, and you could say LDA comma 42, and you don't need the hash because generally you're assuming that if it's not in parentheses that a number is being handled as an immediate value. And so and then you can do the same thing. Like you have the subtract without carry, just the plain subtract instruction can take that just has an immediate operand for it. So you can say, I'm going to subtract 123 from whatever's in the accumulator, and I don't care what the carry bit's set. I'm just going to assume the carry bit is set and just go ahead and subtract 123. And then you have extended immediate. So these are 16-bit immediate values, and these kind of fall into a couple camps. So there's 24 opcodes. 3% of the instruction set are these extended immediate instructions, extended immediate opcodes. And so you can have things like where it is properly immediate, like say BC, that you don't generally, but you could use that to store an address, but it could just be a 16-bit value. And so it's not necessarily an address. So just put 1,234 into BC, and there you have it. It's there. But say for the index register, most of the time it's not terribly useful, although if you just use it as just a place to store a 16-bit value, I suppose you could, but generally you're going to be storing an address to IX. But either way, it's really still immediate, where like before with the 65C02, you would still do these sort of immediate loads of labels. And say you're loading the high byte of the label and then the low byte of the label, and then storing those off into say a 0-page pointer, where you're going to do sort of like you do an indirect kind of operation. So yeah, instead, here we also call things like call and jump, where you have an immediate address there. And so it's still considered the extended immediate mode, but it's more like the absolute mode in the 65CO2, where this is most definitely an address, and the only place that that address is going is into the program counter. And of course that's fleeting. It's not a value, a 16-bit value that's going to stick around in one of the other general purpose registers. So let's take a look at absolute mode, because in 65CO2 we got a lot of them. We got 29 different opcodes. So like 13.74% of the opcodes are using absolute addresses, and they're using them, for things like loading and storing. So we're loading from an absolute address into A, and then storing that to another absolute address, but then using also that absolute address as the target of jumps and jump to subroutine instructions. So you can jump to hex 23C, and that's considered an absolute addressing mode in the 65CO2 instruction set. But with the Z80, it's more complicated than that. So you have that extended immediate addressing mode we just talked about, and there's a bunch of opcodes, but 17 of those, fully 17. There's 22? Maybe I'll go back. No, 24. So out of those 24, 17 of those opcodes can only be interpreted as an absolute address, because those are going into the program counter. You're not going to want to put just some random 16-bit data in the program counter. You're going to want to put the address of an instruction in a program, right? So those are things like call and jump. So instead of JSR 23C in 65CO2, that is an absolute addressing mode. It's an extended immediate addressing mode to do a call 23C and getting the exact same result at the end of the day. But then we have the extended, or it's sometimes called the direct mode. And here there's only 10 of those opcodes, and those work more like the load store absolute opcodes that we have for the 65CO2. And so it's really constrained. So rather than say 13%, it's only 1% of our instructions can do this. So it's really constraining how you actually get data in and out of memory. So you say you could, and you put that address around in parentheses, then say if you're doing like a load A, comma, and then in parens an address, you're going to load a single byte from that address, and then that's going to be stored in the A register, in the accumulator. Then going the other way, we don't have a store instruction in Z80. What we have are basically it's all loads. You're just copying values between registers and other registers and memory addresses. It's all just load. So here you have load, and then the first operand. Of course, the first operand is always the destination. And so at the address 5678, we put that in parens and then comma A to say, all right, we're going to take the value that's currently in A and then store that at the address 5678. And so that'll be effectively the same as the STA 5678 in the 65CO2. But we can also do this with 16 bits of data as well. So we can see here we can do a load of HL to 9ABC. And so there we're going to take, we're not dealing with HL as an address here. We're dealing with HL as just a regular 16-bit value, even though generally HL is going to have an address in it. But could be like you're filling in a jump table somewhere, right? So you're taking the 16-bit value in HL and storing that those 2 bytes starting at 9ABC. So 9ABC and 9ABD are going to have L and H respectively. And then, of course, you can go the other way where you could have a 16, or I'm sorry, did I get that right? No. So yeah, HL is, of course, the target. So here where we would have at 9ABC, we would have an address most likely, or just some 16-bit value. And we're storing that in HL. So that 9ABC goes into L and 9ABD, that byte goes into H. And then it's the other way around. So if you have that address in parens first as the first operand, then that's going to be the destination. So here we're taking what is most likely just a regular 16-bit number and just storing that at DEF0. So whatever's in B goes into DEF0, and what's in C goes into DEF1. And oh, sorry, no, actually, no, it is the other way. So DEF0 is what's going to get C, and then DEF1 is going to get B, right? Just like before. So high, low, B, C, same deal, right? I said it's unscripted, right? This is what you're really here for. So now, of course, we have the 0-page mode and 65CO2. Fully 41 of those 211 opcodes, 19.43% of the opcodes are dealing with just simply a 0-page address. It's the most common addressing mode in the instruction set. And so you have things like load A with the contents of 0-page address 34. And there's just a ton of them, right? There's 41. It's a lot. Meanwhile, in the Z80 land, well, do you mean page 0, right? They switch that around. And so, but really, if you're going to deal with a page 0 address, there's none of the instructions that have actual machine code operands. Of course, we saw that special case with RST where it's encoded in the opcode. But if there is going to be an arbitrary page 0 address, that's going to have to be in your program as a fully 16-bit address, and you're just going to have to suck it up and have a 0 byte in your program code as part of your instruction. So to do a 0-page load into accumulator, instead of doing LDA 34, you'd have to do LDA parens 0034. And yeah, so that's that's what you're stuck having to do. But again, you've got a lot more options, right, with the Z80. But you don't have the option of just cramming a bunch of stuff in the 0-page and making it real fast, other than like a little jump table to use with the RST instruction. Now, one of the few addressing modes that is pretty much the same in both instruction sets is the relative addressing mode. Of course, it's much more prominent on the 65CO2. We have 9 of those opcodes, so over 4% use the relative addressing mode. And you really have to use relative addressing mode for all of the conditional branching, like BEQ. You can use a label, but it has to be a relative label. It can't be an absolute address. It has to be either 128 behind or 127 ahead of the next address of what the following instructions address would be. But for the Z80, you only have 6 opcodes because it's a much more limited use case. Generally, you're going to use the full absolute address, even for conditional branching. And of course, we call that just relative jumping in Z80. So the jump relative can use a relative label, so it has to be within that. So if you're doing JR, say like if the Z bit is set and you want to go to that label, if it's a close enough label, if it's within that bounds of minus 128 to 127 of the next instruction, you can use JR. But if that fails, because that label's too far away. Unlike with 65CO2, if that was a conditional branch, then you're out of luck. You have to kind of work things out. But if it's a JR in Z80, well, just change it to a JP, just a regular absolute jump, and everything's fine. And it will take another byte. It will be slightly slower with the JP compared to the JR, but you can suck that up. And then there's one weirdo instruction in Z80 that has no equivalent that can use a fully absolute address. It only uses relative addressing, and that is the decrement, then jump if not 0. That's the DJNZ instruction, and then its label that has to fit within that relative space. You can't just do a DJNZ with a 16-bit address. So you just can't do it. So that's it for relative. It's relatively similar, but now we get into some of the weirder stuff. So the absolute indirect mode, and actually the same also goes for the absolute 0 page mode, is that these are only like one-off things. So for 65CO2, for absolute indirect, there's only one instruction that uses that, and that's the JMP function, the jump function, where you could have an address somewhere, some arbitrary place in memory, and that will have the address of an instruction to jump to. And you can't do that in a single instruction. There's no instructions like that. And there's a few other instructions that do that with 0-page addresses in 65CO2, but nothing like that exists for the Z80. So if you're going to do indirect, you have to use an address register like HL. Generally, HL is what you're going to use. And so you would, if you wanted to do an indirect jump to 314, which if those of you playing at home may remember as the Commodore / Commander X16 IRQ vector in RAM. And so in the ROM code for the Commander X16, there is that instruction, jump indirectly to 0314. But here, what you'd have to do is load that address into HL, and then we could do an indirect. So we would say, all right, just go ahead and then jump to the address that's at 0314. And that's how that would work. And because 0314 is stored in HL, so whatever address is in HL, I can just jump to that. Or rather, I'm not jumping to that. I'm looking that up, right? So now let's get into the index modes. Now, of course, it's actually more complicated on the 65CO2 side for the index modes, because there's 7 different index modes. And so you're doing a lot of indexing, like the absolute index with X, 17 opcodes. So that's like where you have just some address, an absolute address somewhere, and then you're just adding the value of the X register to that address, and then you're loading from that place in memory. And then you can do the same thing with the Y index. And you can also do in both cases with the 0 page. So you can see here all of these opcodes that are just taking X and Y and just adding them to an address that's put in your operand, and either a single byte 0 page address or a fully 2-byte 16-bit absolute address, and then using those index to add to that sort of hard-coded address, as it were. But then for things that are maybe a little less hard-coded, you have indirect ways of indexing, the zero-page indexed indirect, where you're expecting on the 0 page to have a jump table. So you have a bunch of addresses that are on the 0 page, and then you use X. X better be an even value, right? If it's an odd value, you're going to get some funky, invalid addresses possibly. And but you still have 8 opcodes for something that hardly anybody uses. But still, 3.79% of that 65CO2 instruction set is dedicated to this mostly useless addressing mode. But there you have it. Now, the actual useful addressing mode, the 0-page indirect index with Y, where you can just take up 2 bytes of the 0 page, put a 16-bit address in there, and then use that. Then use the Y index register to then index from that in RAM, and then that would be just like using the absolute indexed modes, like absolute index with Y, but you don't know what the address is, so you can programmatically determine that absolute address and then place that somewhere on the 0 page. Just take up those 2 bytes. So much simpler, right? But the folks at MOS felt it was just as important as the practically useless 0-page indexed indirect mode. And then the folks at WDC that took over and built the 65CO2 created an entirely new indexed mode, the absolute indexed indirect mode, where it is like that very useless 0-page indexed indirect, but there's only one. It's just for the jump instruction. And this is a little less useless because this doesn't have to take up that precious 0-page space. You can just have a jump table anywhere in memory, and then you can, again, you're going to want to have X be an even value, and then you can jump to an address. And that's actually turns out to be a very useful instruction and a pretty nice addition. So kudos to WDC for that. Now, meanwhile, we're still talking about indexed mode. And for Z80, it's actually less complicated. And rather than with 7 distinct index modes, there's really, it's just considered a single indexed mode in the Z80. But there's really 2 submodes, right? So if you're talking with the 65CO2 or it's just regular 6502, the Y-based and X-based are the indexing are considered separate addressing modes. So we'll call them submodes. Again, this is just my interpretation of the instruction set, and this is all I call them submodes. So basically, you have the one submode is relative to the IX register. And so as you can see, it's used entirely differently. This is an entirely different concept than the indexing with 6502. So here, what I would have is the actual address is going to be stored in IX or in IY if it's the relative to IY submode. So I have one of my index registers, rather than just being an 8-bit addition to some other address, it's going to be the address itself in the index register. And then I'm going to have a relative offset. Again, just sort of like the relative address modes, this is almost like indexed relative, right? So it's really more of a relative type addressing mode than a proper indexed addressing mode, as we would understand it from the 6502 instruction set architecture. So what we would have is either a plus or minus value. So we're saying we can't use a label like in a normal relative addressing mode either, but it's the same range. It could be minus 128 to plus 127. And we can just say whatever the value is in the index register, I'm going to add or subtract an offset from that, and that's what I'm going to be using. So there, and again, these are all of these indexed modes are used for doing memory I/O. So I am going to take the memory address in IX and add 1 to that, and the value of that address is what I'm going to load into A, or I'm going to take I'm going to take that address that's in IX, subtract 2 from it, and then that's going to be the destination of the value that's in the B register. And then I do the same things kind of with the C and D registers, but with IY. And ultimately, you could just have 0 as your offset. So you can just use IX or IY as a straight up indirect register, just like HL. But HL doesn't let you do this, the plus and minus business. You have to use IX or IY. So now you have perhaps the weirdest addressing mode. It's the doubled up addressing mode. And of course, this is something like this would be perfectly normal in the Z80, where of course you have 2 operands that have different addressing modes, right? What's weird about that? Well, that's very weird when you're talking about the 6502. And this was an addition specifically for the 65CO2. But there are 16 opcodes that are using this. And again, they're pretty limited in scope of how they're using it. And if you were to think about them in a Z80 context, there's really 3 addressing modes at work, because it's also using the bit address, what we would call the bit addressing mode in the Z80. So you have like BBR, so branch if bit reset, and then you have 0 through 7. And branch if bit set, also 0 through 7. But again, you don't have a space there before the bit number. That bit number is just appended to the actual instruction name abbreviation mnemonic. And then you have a 0-page address, and then as the first part of your operand, and then another operand that's going to be a relative label. And again, so that label can't be too far away or this will fail. So it's got to be within that minus 128 to plus 127 range. And because each of these opcodes, you have these 16 different opcodes, that means that you got 8 of each of them. So yeah, that bit number is encoded within the opcode, and then you just have 2 bytes of operand data. So again, you're not going beyond the normal bounds of a 6502 instruction, and you're effectively getting 3 arguments out of it. What would be like 3 assembly language operands in a Z80. So yeah, so Z80, yeah, this is a weird addressing mode. We don't have something like this all put together. So if you were to do, say, a BBR5 34 label, like that first example, you'd have to do that in 3 separate instructions in the Z80. So first you would have to load address 34, and you'd have to load the full 16-bit address into HL. So already you've hit that that 3-byte limit, right? So you've got a lot more to a much larger amount of program data to take up to do this operation. But again, how often you got to do it? I don't think I've ever used any of these, right? If these were available, say for the Atari 2600, where you've got everything on the 0 page, oh my goodness, you'd be using it all the time. But it's not available for the 6507, so yeah. But anyway, to do that BBR example, after you load that instruction in HL, then you could do a bit 5 on it, using it as the indirect memory-based register, and then you could save a little bit by doing a jump relative, because that, if assuming that label is going to be just as close by, you could do a jump relative. So if Z is set, then jump to the label, and so there you go. That's how you do this weirdo thing in Z80. If you would ever do that, who would? I don't know. So here we go. So what's my conclusion? Well, I've been doing this 6502 thing for a while. It's been over a year and a half since I've been creating content. It's coming up on 2 years soon that I've been making games for the Commander X16 and the Atari 2600 using the 6502 and 65CO2 instruction sets, and 6507 really, Atari 2600, which is even further constrained. And I've become very comfortable in that, and it's very easy to learn, even though there's some weird concepts in it. Some things are kind of hard to get your head around, but at the end of the day, you only have 211 opcodes, and a lot of them are of that same instruction. So there's not a lot of different instructions. The instruction mnemonics are very simple, but I mean they're limited. It can be very fast, especially if you're kicking it up to 8 megahertz, like with the Commander X16. But you're going to have to just trudge through a lot of code to do a lot of basic stuff. Some things that in other instruction sets, you're not going to have to write a ton of code to do this stuff. And I think that's where Z80 really takes the upper hand, is that it's got like everything in the kitchen sink in there. It's properly CISC. You're not really getting a lot of the benefits with the 6502 for being RISC-like, because you still have variable width instructions, and you don't have proper pipelining, other than, like, I guess when you're finishing up one instruction, you're prefetching the next instruction, but that's not real pipelining like you would have in a modern RISC processor like the ARM. And I mean, still the Z80 is very primitive when you compare it to a modern x86, especially with a 64-bit architecture. It's still very, very simple compared to that. I would much rather do Z80 coding than x86 coding. Far simpler to deal with. But it still kind of comes up as a toss-up, because part of the reason of doing this 8-bit programming is because it's so simple, and the 6502 is just really, really simple. But it'd probably be a bit frustrating, and I think you could be a lot more capable and get a lot more done, and really have a more impressive, more professional kind of product that comes out of the Z80. And that's, I think, why the Z80 was really used, at least initially, in a lot more of these professional systems, like the K-Pro and the Osborne and the original TRS-80, which, of course, different from the TRS-80 color computer. Don't confuse them. The color computers are based on a completely different architecture. Those used Motorola 6809 based chips, so incredibly different. But the Z80, you could really conceivably have a sophisticated operating system like CP/M that would, be able to really do a lot for you. And so I would think that if you're going to have a proper grown-up system to really have a lot of capability, I think the Z80 is a better choice. But again, it's a matter of what your purposes are for there. And I think the 65CO2 still really works as the better option for the Commander X16, because you're reusing the Commodore kernel, and I think it's a lower barrier of entry for a beginning assembly programmer. And why I'd also probably recommend folks go and look at my Commander X16 assembly tutorial before they look at what, and it hasn't started yet, so you've got time. It's going to be probably still like a week and a half before the first episode of that comes out. But I'll have maybe one or two other Z80 related videos before that. But I think if you're just starting out in assembly language, I would recommend the 6502. But if you really want to make something like very fun and exciting and highly capable and complicated, and being able to do more complex math and other stuff and data processing, I would go with the Z80 for that. So then now I just leave it up to you. And so please put your comments in there. Let me know what you think. And meanwhile, I'm going to load up the folks who really have a great ability to give me a lot of feedback, even before these videos come up, which are my patrons on Patreon. So if you want to join that community, click the link that's in the description, or it's right here, patreon.com/SlivyMatt. I'm SlivyMatt on all social media also, and on GitHub, and everything you can think of, that's me. And if you are a Patreon, you'll get notified as soon as my videos are done, even before they go out to the public. And you can get that for as little as $1 a month. But otherwise, if you don't need to. I'm providing all of this content, all this public YouTube content for free. Of course, I have advertising on there. I have a monetized channel, but you can just subscribe for free and click that bell to get notified for free when those videos actually go public. If you can wait until then. So if you're impatient or generous or whatever, please hit me up on Patreon and come join the community there. We got a lot going on. We've got also exclusive content that you're not going to see on YouTube unless you're a patron. So I thank you, and please let me know what you thought of this video, what you hope to get out of the tutorial series that's coming for the Z80, or what you've already gotten out of the 65CO2. And if you are familiar with both of these instruction sets, what are your thoughts? Have you done significant development in both of them? Let me know what your stories are. Just put them right down in the comments, and I'll take a look, and I try to respond to as many as I can. And although this is as popular as the first Z80 video, I might not get to all of them because that's really done well. And I thank you all so much, and I'll talk to you again soon. Bye-bye.